All right. Hi, folks. This is my first of two lectures on liquids, solids, and solutions, which is chapters 11 and 13 in the Brown textbook. Here we have assistant and audience member number 2.
He's a starfish.
He's not a starfish.
Oh,
He's not an echinoderm.
are you sure?
His skin is smooth. All right. A few lectures ago, we were talking about gases and discussing the kinetic molecular theory and how for gases, the molecules bounce all over the place and don't have strong interactions. That's one of the assumptions for the ideal gas law, neener. And when you get really down into it, and you look at the list of assumptions for ideal gases, it says, there are no attractions between molecules. And then later on, there's a van der Waal equation that says actually there are some attractions between molecules. That's a lot of what we're going to be talking about is van der Waal forces, which are attractions between molecules, which there are small amounts of them in gases, but they're kind of overridden mostly by the fact that they're bouncing all crazy. But when you get down into liquids and solids where they're moving much more slowly, there I am yawning again, it's late. The van der Waal forces, the intermolecular forces, are keeping them closer together in the liquid and the solid state. So with the liquids, those molecules are moving more slowly. They're only in the bottom of the container, and those attractions are more important than they are in gases. And in fact, they would need to be overcome with some amount of energy in order to vaporize the liquid. Same with solids. The molecules are moving even less. They're in a rigid shape. Although they are vibrating, but there's no translational motion. And the attractions are even more important, and they would have to be overcome to melt. And one thing that's important to know is that apparently they call melting fusion. And so, yeah, I know, right? And so if you're looking for the value for, well, how much energy does it take to melt this thing, you have to look for your delta H of fusion. Which is totally bizarre, but fusion is melting, okay? All right. So those attractions that are the intermolecular forces, they're also known as van der Waal forces. He showed that it was silly to assume that there aren't any forces in gases. That's even more true in liquids and solids. They play a really large role in the physical properties of your liquids and your solids, like what your boiling point is and how your proteins fold and how hard the substance is and all that kind of junk. So let's run through the different types of intermolecular forces. Basically, we have dipole forces and London dispersion forces. Those are the two main types. There's one fancy type of dipole forces called hydrogen bonding. We'll get there. So dipole forces are an attraction between two polar molecules. So if you've got two water molecules, for example, near one another, you've got the negative charge on the oxygen and the positive charges on the hydrogens, because the oxygen is more electronegative and is pulling the electrons toward it. So oxygens end up with a partial negative. So those two negatives will repel each other, but a negative and the positive end of the next one will attract. And that forms, that is two poles attracting each other. So that's an example of a dipole force. And in fact, with water specifically, that's an example of hydrogen bonding. The strongest type of dipole forces, number 2, is hydrogen bonding. And the reason that hydrogen bonding is the strong type is because the hydrogens are a pretty low electronegativity value, whereas with nitrogen, oxygen, and fluorine, those are the three that matter. If you have a bond between nitrogen, hydrogen, oxygen, hydrogen, or fluorine, hydrogen in particular, those very electronegative elements will suck those electrons pretty hard, and so you have a serious example of a polar bond. So the hydrogen bonding is the strong dipole force. Bing. And it's important to remember that it's those three elements that do it. NOF. NH, OH, and FH bonds will give you hydrogen bonds. And you'll have to identify that probably from a list of things. Which of these have hydrogen bonding? And you're like, well, it's N, O, and F. la da da. Okay, so that's a type of attraction that's only present in polar molecules, and so then you kind of go, well, what about all the regular molecules that aren't polar? Um, it turns out that actually all molecules experience this kind of force, which is the London dispersion forces. Sometimes they're just called London forces. Sometimes they're just called dispersion forces. Sometimes they're called London dispersion forces. They just mix it up a little bit, but they're all the same thing. These are the forces that occur in all molecules, and the way that they happen is through a thing called an induced dipole. And induced dipoles these aren't polar, but it just so happens that if the electrons kind of happen to end up on one side, then they have a negative side and a positive side very briefly. And that molecule sitting next to molecule number 2, when you have that brief dipole here, so here you end up with, say, 3 electrons on the right-hand side and 1 electron on the left-hand side, you're like, oh no, this side is more negative now. Well, that means that it's going to repel his neighbor's electrons to that guy's right side. So you cause it, this first one will cause the second one to have poles, just through kind of a coincidence of the electrons being on one side versus the other. And those are brief forces. They're temporary, and they'll go away as soon as the electrons go back to the way that they normally are, where they're kind of balanced around the molecule. So that's London forces. When you're only dealing with kind of small molecules, it ends up being a weak force. The larger the molecules get, the more electrons you have, and the more likely it is that they're going to be unbalanced. And so, large molar mass molecules can actually have pretty strong London dispersion forces that can be stronger than dipole forces. Typically, a dipole force, like an individual one, is stronger than a London dispersion force. But if you have a whole bunch of them and it's big, then your London dispersion forces can outcompete your dipole forces. If you have dipole forces, you've also got London dispersion forces, because every molecule has got London dispersion forces. So, like with water molecules, you've got hydrogen bonding, and you've also got the London dispersion forces. Another thing about London dispersion forces is if you're trying to make a comparison between 2 molecules and they're asking, which one is going to have stronger London dispersion, basically it's which dude is larger. You can also consider the shape. If they can line up, if they're kind of long molecules and they can line up next to each other, you can have London forces kind of up and down all the way along. So that contributes to stronger London dispersion forces, as opposed to molecules that are kind of in tight balls. So you have to kind of think about the shape of them. And then also, if you've got pi bonds with those extra electrons on the outside, those are very polarizable, which you can make them polar. They are polarizable. So the more polarizable something is, the stronger London dispersion forces are. So pi bonds are more polarizable, and large molecules are more polarizable. So this has an effect on your physical properties of liquids and solids, like your melting point and your melting point. Do you have your phone on, assistant? Maybe. So if you look at this little chart here, we have got a list of all of the halogens in their diatomic form: fluorine, chlorine, bromine, and iodine, and the molecular weight in their in AMUs, 3871. So it's increasing as you go down. And what you can see is that the boiling point also increases. So you can see what's happening here with the increasing molecular weight is that you've also got increasing boiling point, and that is caused by the increasing London forces between all of these molecules, because as they get heavier and heavier, that sort of indicates that they've got more and more electrons, which means that they're more polarizable, and that means that they're going to have stronger London dispersion forces. And with stronger London dispersion forces, they're held together longer even when they're getting warmer and warmer. So typically the higher temperature would make them capable of breaking free of the London dispersion forces, but when the forces are stronger, it requires more energy to do that. So, iodine doesn't boil until 500 degrees Kelvin, whereas it is hot. Whereas fluorine boils at 85 degrees Kelvin. That's cold. So what you can see on the periodic table is that, fluorine and chlorine are gases at room temperature. Bromine is a liquid at room temperature, and iodine is a solid at room temperature, and that's due to your increasing molecular weight affecting your London dispersion forces. So, and you get the same deal with your noble gases. You've got them helium, neon, argon, krypton, xenon, heavier and heavier and heavier, and higher boiling point. And one thing that's interesting actually is, you've also got melting points that are below the boiling points, because you can have solid xenon when you get really cold, and solid krypton, and solid argon, and solid neon. There is no solid helium.
Really?
It doesn't ever freeze.
Huh.
The boiling point of helium is 4.6 degrees Kelvin.
Got it.
So, liquid helium is really dang cold under atmospheric pressure. And so, with it being that cold, that it don't make any sense. So it's liquid at 4 degrees Kelvin, because what you've got going on is it's only got 2 electrons, so it's not very polarizable. And so the London dispersion forces are actually really weak, and they're only strong enough to get it to a liquid state. They're not strong enough to get it to a solid state, even when it is that cold. And then another thing that is important to know is the relative strength of all of these different attractions. The strongest attraction that there is an ionic bond, because you've got a totally positive charge and a totally negative charge being attracted together. So that's why you've got the really hard ionic compounds, and they've got the really high melting and boiling points. After that, you've got covalent bonds. Those are not quite as strong as ionic bonds, so they're slightly easier to break than the ionic bonds are, and you've got slightly lower melting and boiling points for covalent compounds. And then with the intermolecular forces, forces that are between different molecules, the strongest individual one is the hydrogen bonds, which are the strong form of the dipole-dipole forces. And then the London forces is sort of hard to say, because, when you have a really, really, really big molecule, the London forces will get very significantly strong. But in general, if it's just sort of a small, regular, typical molecule that we would consider, then they would be maybe equivalent to or slightly less than the dipole-dipole forces. So that is the intermolecular forces, also known as van der Waal forces. Bing. All right, and then we're going to think about solids themselves. Your two main types of solids is an amorphous solid and a crystalline solid. Amorphous solids are your mushy solids.
Mashed potatoes.
Mashed potatoes is sort of a mixture.
No.
Anyway, you're being complicated.
Thank you.
So you've got mixes of particles, large complex molecule particles. So, rubber or glass, or like chicken or something made of long proteins and cells and junk. But it's got variable composition, and what's interesting about amorphous solids is that they don't have specific melting points, because they have a variable composition. It's not a specific thing, and so they will soften over a range of temperatures, instead of what happens with typical crystalline solids. You will warm them up, and you can watch them, and they will go bam and melt, instead of going kind of like rubber would. So that's an amorphous solid. And down here we have kind of a visual representation of the craziness that an amorphous solid is, which is just atoms all over the place, and they're kind of bonded together with some bonds and London dispersion forces, and that's what's holding it together okay. Crystalline solids are organized solids, and you've got a 3-dimensional lattice structure. where you've got specific particles at the points of your lattice, and they are bonded together by one thing or another. So, and you've got different kinds of crystalline structures based on what types of things are at your lattice points and what the attractions are between the pieces. So you can have atoms at your lattice points. So let's get into it. So you've got atomic crystals or molecular crystals or ionic crystals. And so the difference here is that an atomic crystal is at each of the points you have an atom. So for example, in this crystalline structure here, which is kind of, they're showing you the cube shape of it, you've got an atom, an atom, an atom, an atom, an atom, an atom. And so that's an atomic crystal. If you have a molecular crystal, you're talking more about something like water or dry ice, where you've got your lattice structure, and at each of the points you have a molecule. So a water, a water, a water, a water, a water, a water. Or with dry ice, you've got a carbon dioxide, a carbon dioxide, a carbon dioxide. So that's slightly different, where you've got an atom or a molecule at each of the lattice points. And then you've also got your ionic crystals, which we've actually talked about before, like salt, where instead of having an atom at each point, you have an ion at each point. So 2 types of solids, amorphous and crystalline. 3 types of crystalline solids, atomic, molecular, ionic. And now there are 3 types of atomic.
Oh no.
Yeah, I know, right? So for an atomic crystal like diamond, what you have got is carbons at each of the points, and the connections between those carbons are covalent bonds.
Okay.
And those are really strong. And so a network atomic solid tends to have really high melting points and high strength and high hardness and stuff. And that's why diamond is so hard. It's uniquely extremely hard because the connections between the points of that lattice structure are covalent bonds, instead of, for example, with ice, the connections between those lattice points is hydrogen bonding, which is a lot weaker. You can also have metallic crystals. If you melt metals and then cool them slowly enough, they'll kind of arrange themselves into a crystalline structure. And the crystalline structure that it's in determines kind of how strong the thing is. And so, like, I read something about the steel that they use for cars. They have made serious advances in the way they crystallize the steel that they use for the metal in cars, to the point that, like, the steel is now so strong that the in the newer cars, that the jaws of life, like the dudes that cut open the cars, can in some cases no longer cut through the steel.
No way.
And they're like, sorry, dude, trapped in the car. So yeah, there's crystalline structure to metals, which you don't really realize, but there's crystalline structure to metals, depending on how you've done it. So in a metallic crystal, the points on the lattice structure are metal atoms. And the thing that they say about metallic bonds, it's a type of covalent bond between the metal atoms. So it's actually pretty strong, a strong kind of structure. The electrons are, quote, delocalized in a sea of electrons, because the valence electrons in those metals can just kind of flow all over the place with all those metals, which is why they're good conductors. And so you've got metallic covalent bonds, delocalized electrons, and they form a crystalline structure. And then the other thing you have to think about is that metallic bonds also are involved with alloys. So what I was talking about with steel is an alloy of iron with little carbon atoms in between. Here's a picture. You've got a metallic bonds with the interstitial alloy. There's 2 different forms of alloys, the substitutional alloy and the interstitial alloy. A substitutional alloy is you take one of these big green atoms and you replace it with a different one. So you might have a mixture of zinc and copper or whatever, and I think that's brass. And so you've replaced one of the coppers with zinc. That's a substitutional alloy. An interstitial alloy is, hey, there's enough space to fit a little tiny atom in between these guys. And so that's what steel is. Steel is iron atoms with carbon atoms crammed in the little spaces in between them. And you've got metallic covalent bonds there. So there you are. And then the third kind of atomic solids are the group 8A, which I think is a great name, right? Those are the noble gas solids that I was talking about here. Here. The below helium, though, you don't get solid helium. And the only attractions for those are the London dispersion forces, which get stronger and stronger the heavier you get. And they have a very low melting point, as you can see over here. The boiling points are pretty low. The melting points are even lower. All right, so those are atomic crystalline structures. Molecular crystalline structures, you've got whole molecules at the lattice points, such as ice with H2O, and strangely sulfur. The element sulfur goes around in little groups of 8 sulfur atoms, sulfur molecules. Yeah. And so sulfur makes these fun crystals with S8s at each lattice point, and they make pretty hexagons and stuff. Octagons, probably.
Yeah.
Let's say. Dry ice is another one. And so these whole molecules are connected sometimes with dipole-dipole forces if it's a polar, or hydrogen bonding if you've got OH, NH, or FH. But in the example for sulfur, you've got London dispersion forces only, where the other guys have London dispersion forces as well, but they're not as important when you're the dipole-dipole. And then the last form of your crystals are your ionic crystals. So your ionic crystals is you've got the ions at the lattice points, and these are the normal ones. So like sodium chloride, you get the nice cubes. The bonds are really strong, and so they're really hard to break with your melting points and your boiling points. So these have got the highest melting and boiling points when you're trying to break those ionic bonds, and they're really hard and brittle, etc., etc. Okay. And next, physical properties of liquids. As we've been talking about, the boiling point and the melting point, for example, are affected by how strong your intermolecular forces are. And you have to think about the boiling point as the temperature at which those intermolecular forces are finally overcome. And the same thing with the melting point, the temperature at which the intermolecular forces are finally overcome. But from solid to liquid is not as large of an overcome, because all you've got to do is get them to slide past each other. Whereas with the boiling point, where it goes from liquid to gas, you have to get the molecules to actually totally separate from one another. So that's why you tend to have, it takes more energy to boil something than to melt something. So there we go. There's that. And then there's also this thing, vapor pressure. Vapor pressure is the gas pressure that you get when you've got a liquid in a closed container. So if you've got like a gas can, and you ever open it and you sniff it, you're like, oh gosh, seriously, gasoline. That's because what has happened is that a lot of the gasoline has evaporated into the space above the liquid surface and put a lot of vapor into that gaseous area. So there's a certain amount of pressure that's being contributed by that. It's like the Dalton's law of partial pressures. Some of the pressure is being contributed by like the regular atmosphere, and some of the pressure is being contributed by the fact that there's gasoline vapor above in your gas can. Have you ever left a gas can in the sun?
Yes.
What happens when you open it?
Boom.
Yeah, it goes psss. Because basically the only thing that affects your vapor pressure for a given liquid is the temperature. Because if you heat it up more, then more of the particles will overcome the intermolecular forces in order to go into the vapor phase and evaporate. So, it doesn't matter like the shape of the container or the size of the container, how much gasoline you've got in there. It's always going to contribute the same amount of pressure based on the temperature for that particular liquid. So and then the other thing is, the stronger your intermolecular forces, the lower your vapor pressure is going to be.
Yes.
Because the intermolecular forces will keep it together longer. So that's why gasoline, which is a non-polar molecule, which is mostly octane, it's a mixture, but okay, let's say it's octane. The non-polar molecules, the only forces keeping gasoline molecules together are London dispersion forces, which are not as strong in normal size molecules as, for example, water, which is polar, and has the hydrogen bonding. So that's why gasoline is volatile. A lot of it evaporates away. It has a high vapor pressure because it's got lower intermolecular forces. Another thing that's affected by your intermolecular forces is your surface tension. Have you ever done that thing where you've got a penny and you put drops of water on it?
No.
Oh, I should do that with my class.
Ooh.
You can get a penny and you can put a drop of water on it and a drop of water on it and a drop of water on it and a drop of water, and you're like, okay, I can maybe get like 5-6 drops on there. You can get way more than that because because you end up with this, you have to be careful and not like knock it or whatever. You can get this nice like rounded, beautiful kind of semi-sphere of water just sitting perfectly on top of that penny because there is a cohesive force between each of those water molecules that's pulling it in and trying to make it spherical. That's your surface tension. That's why water beads up, because it's got the strong intermolecular forces. You see this in water. You also see it in mercury, which we haven't played with as much, I think, now that we're not trying to poison ourselves like they did in the 50s. But mercury also exhibits this, cohesive force, the surface tension, pretty strongly because it's got metallic covalent bonds, like we were talking about up there. And those are covalent bonds, which are pretty strong. Then another similar thing is capillary action, which is like if you have a thin glass tube and you stick it in a real thin glass tube and you stick it in water, the water will go bloop and climb up above the regular surface of the water. And you can also see this in the shape of the meniscus in a graduated cylinder where it goes boop. What's happening is that the water has got an adhesive force. It's attracted to the glass molecules. And that adhesive force is actually overcoming the cohesive force to some extent, so it's climbing up that glass. What's interesting is that the mercury, when you put mercury in a graduated cylinder, it doesn't go boop, it goes boop, because its cohesive force, its surface tension is very, very strong with the covalent bonds, and it doesn't really have an attraction to the glass molecules. So you have an upside down meniscus with mercury, and a dippy meniscus with water. So I thought that was kind of cool. So mercury beads up even in small tubes, whereas water, meniscus that's a verb. And then more on vapor pressure. What happens with your vapor pressure is that, first, let's say this is a container of gasoline. I know it's blue, but it's gasoline. And you put a cork in the top of the container, and it's got to be a closed container, because it won't ever come to an equilibrium vapor pressure if it's open. It'll just evaporate and all go away. But if you close it, at first what's going to happen is that some of that gasoline is going to evaporate. So it's going to evaporate, 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 evaporate. And then at some point, you're going to reach your equilibrium vapor pressure. The vapor pressure, how much of it likes to be evaporated at that particular temperature. If it's hotter, it's going to have a higher vapor pressure. If it's colder, it'll be a lower vapor pressure. But at that particular temperature, it will reach equilibrium. And what ends up happening is it'll go evaporate, condense, evaporate, condense. One will be going out while one goes in. So it's not like it evaporates and then stops. It's that it will reach an equilibrium point where the amount that's evaporating is the same as the amount that's condensing. So that's the point at which you have found your vapor pressure. And this is from that Dalton's law of partial pressures. So it increases with temperature because more molecules have the minimum energy that is needed to escape. And again, if you've got this is related to your intermolecular forces. If you've got a larger molar mass, you've got stronger London dispersion forces, and so it's got a lower vapor pressure. And what's interesting is that going back to boiling point, the definition of a boiling point, of your standard boiling point, is when your vapor pressure gets to 1 atmosphere. Because let's say you're trying to boil some water. Well, what are you trying to do? You're heating up this water to overcome the intermolecular forces between the water molecules so that it can become a gas. Well, it's being pressed down on by your atmosphere. And little bits of water are evaporating in order to with the vapor pressure of water. As soon as you get it warm enough that the vapor pressure has reached 1 atmosphere, now it's not being squished down to prevent it from evaporating, to prevent it from boiling. So you make it hotter and hotter and hotter, and the vapor pressure increases. As soon as it hits 1 atmosphere, that's your boiling point. So that's kind of cool. Which is why when you go up to the top of the mountain and try and boil water, well, the atmospheric pressure is lower up there. And so your vapor pressure will reach atmospheric pressure sooner. You don't have to get it as warm to overcome the atmospheric pressure. So that's why water boils at lower temperatures at the top of mountains, which is why they have different baking instructions for high altitude baking, which is kind of cool. And then the other thing to remember is that your vapor pressure is affected by solutes. If you remember back to colligative properties like boiling point elevation and freezing point depression, if you've got salty water, then it freezes at a colder temperature, it boils at a higher temperature. Those are colligative properties. Vapor pressure is another colligative property. If you put salt in water, it affects the vapor pressure and decreases it. Ding. Okay. So now for the questions. Go ahead and do your questions, and I will come and tell you the answers. All right. What type of intermolecular forces account for the following differences? You've got CH3OH, which boils at 65 degrees Celsius, and CH3SH boiling at 6 degrees Celsius. These are very similar molecules, the only difference being the O versus the S. And the reason that this one boils at a higher temperature is because you're ending up with hydrogen bonding with the OH bond, whereas you would only have a regular dipole force with the SH bond here. So that's why it's higher. So that's H bond. Xenon is liquid at atmospheric pressure, whereas argon is a gas. Argon is a gas because of the London dispersion forces being weaker with argon. Argon is smaller, it is less polarizable. So it's got weaker London dispersion forces. Xenon is bigger, it's more polarizable, it's got stronger London dispersion forces. All right, acetone, which is got this structure here with this double bond O, boils at 56 degrees Celsius, whereas 2-methylpropane boils at -12. So that means this one has got stronger forces. And the reason for that is it's polar. It's got this oxygen sticking off of one end. So this is dipole. All right. What is meant by the term polarizability, and which of the following would you expect to be most polarizable? Polarizability is that ability to be polarized, with the electrons being able to be non-symmetrical, ending up more on one side than the other, so you have an induced dipole. So things that are more polarizable tend to be heavier because they've got more electrons. So we're looking for the heavy dude among these, which is, here's my periodic table, nitrogen, phosphorus, arsenic, and antimony. That's antimony. So antimony. Put them in order of increasing polarizability. Again, these are all basically the same structure, a central atom with 4 dudes around him. And so it's going to be, again, based on mass, because you're more polarizable when you're heavier. So the lightest guy is methane, the next one is SiH4, the next one is SiCl4, and then GeCl4, and then GeBr4. Predict the order of increasing boiling points of those substances. So the question is it going to be easier to boil the lighter dude or the heavier dude? And the germanium tetrabromide here is going to be the heaviest one, which means it's more polarizable, which means it's got stronger London dispersion forces, which means it's going to have the highest boiling point. So it's the same order. So the same order. All right. Draw a picture that represents a crystalline solid. A crystalline solid, you've got boom, 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 versus an amorphous solid, which is more like boom, 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 boom.
I like that one.
Yeah.
More fun.
Covalent bonding occurs in both molecular and covalent network solids. Why do these two kinds of solid differ so greatly in their hardness and melting points? Well, which one is harder and which one has a higher melting point? That's going to be the covalent network solid. That's your diamond right there. Covalent bonding occurs in molecular solids in the sense that, like in ice, there's covalent bonding within each water molecule. So that's where your covalent bonds are there. But that solid is being held together by intermolecular forces, whereas the covalent network solid is being held together by covalent bonds. That's why they are harder and have higher melting points. 7. Circle the one with a higher melting point and indicate why. All right. HF has a higher melting point because it's got H bonding and HCl doesn't, because H bonding is with HF, HN, and HO. NOF. NOF. All right. Graphite versus methane. That's going to be graphite. Because that's held together with a bunch of covalent bonds, whereas the methane molecules are held together only with London dispersion forces. So covalent bonds. Here we've got potassium chloride and chlorine. That's going to have a higher melting point because it is being held together by ionic bonds instead of chlorine, which is only going to be held together by London dispersion forces. With lithium fluoride and magnesium fluoride, these are both ionic, so they're both going to have pretty high melting points. To be a stronger ionic bond, this is something that we talked about with yawn number 3?
Number 3.
Yawn number 3. Something that we talked about is that the stronger the ion charge, if you've got a charge of 2+, for example, that's going to require more energy to overcome than if you have a charge of 1+. That's your lattice energy deal. So magnesium fluoride is going to have a higher melting point, and that is a bigger charge. And that's related to this formula, Q1, Q2 over R equals your lattice energy. And your Q's are your charges. So if you have a bigger number on top here, you're going to have a bigger lattice energy, so that's harder to break. Argon and xenon, I think we already talked about this one. Xenon is bigger, so it's more polarizable, so you've got stronger London dispersion forces. Silicon dioxide and carbon dioxide are basically the same. Although if you think about it, silicon dioxide is a solid and carbon dioxide is a gas. So if I had asked you before which one has a higher melting point, hopefully you would have said silicon dioxide because it's a solid. But the reasoning behind that is because silicon dioxide is heavier, and so it's got stronger London dispersion forces because it's more polarizable. G is the same as C, potassium bromide, because it's ionic instead of just London dispersion forces with the bromine. And the C6Cl6 is pretty dang heavy compared to the hexane here, so that's going to be London dispersion forces. Kind of the same answer every time, have you noticed? Find the heavy one. Question 8. The surface tension of CHBr3 is greater than that of CHCl3. That's because it's got stronger London dispersion forces because it's heavier, and that means it's more polarizable. B, as temperature increases, oil flowers. Oil flowers. Faster through a narrow tube. That's because when it's warmer, you've overcome some of those London dispersion forces, and so they can slide past each other. So I don't know what to draw besides a flower for that one. Moving on. Raindrops that collect on a waxed automobile hood take on a nearly spherical shape. Wax is a nice big nonpolar molecule. So when you've got water sitting on it, it doesn't really have any particular attraction for the wax, and so it can focus on its attraction for itself. It's kind of narcissistic. And so those water molecules are pulling in and attracting themselves, and that's why you get that nice beading thing whenever you go out and you do your, what's that? Rain-X on your windshield. You get really good beads. However, if it's raining oil out and you've Rain-X'd your windshield, you're out of luck because the oil will be attracted because of the London dispersion forces between the nonpolar wax and the nonpolar Rain-X and the nonpolar oil. So you would have a nice sheet of oil on the windshield. Yeah.
That's useful.
All right. And here is a graph of 3 liquids with their vapor pressures. Hello, graph. And as you can see, as the temperature increases, the vapor pressure goes up. And we need to identify which one is water, which one is ethanol, and which one is diethyl ether. And looking at ethanol, you have a nice OH on the end here, so you're going to have some hydrogen bonding. But not as much as water, because it's got 2 of them. And then diethyl ether is a nice nonpolar molecule. So diethyl ether is going to be the one with the low vapor pressure, which I can't draw. So that's number 1. And number 2 is going to be ethanol. And then number 3 is going to be water. So that one is water, that one is ethanol, that one is diethyl ether. And my reasoning is that the intermolecular forces with the water are the strongest, and so it's going to have the lowest vapor pressure of the 3. Ding! Thanks very much, folks. See you next time. Oh, wait, no. I realized that there's a really awesome, really good description of London dispersion forces on YouTube by this dude, Bozeman Science. This guy here, youtube.com/watch $V=1I big Y KAJMSYPY. Go there and watch that. It's 5 minutes, and he does a real good job.
Okay.